So using the greatest common factor method to factor a polynomial works great as long as you can look through your polynomial and identify a common factor of all of its terms. But that won't always be the case. For example, we would know what to do, for example, to factor a expression like, I don't know, x squared minus 11x. We would know how to factor this at this point. What would you do? So you would look at these two terms, x squared and 11x, and why is x a good choice? Because they both have it. X is a common factor in both of those expressions. X squared is x times x. 11x is 11 times x. And so, looking right at us here is the greatest common factor of these two expressions, namely x. So we know that we could factor this by bringing out that x. And when I bring out that x, what would be left over after factoring that x out of each of the terms? Yeah. In fact, we can see it from these factor trees that I drew up here as well. It's just the leftovers. The other factors that came together to make x squared and 11x are x and 11, respectively. So that ends up being what's left over. So if this were the problem, we would already know how to do it, right? That's the most that we could do with it. The problem is when suddenly we end up with more than we know what to do with. What if I add in another term into this expression? X squared minus 11x minus 26. Now we're playing a different game. We're playing a different game because the greatest common factor knew how to account for the x which was in the first two terms of this, but it doesn't know how to account for the fact that this 26 doesn't have an x for me to take out. So we're out of luck in using the greatest common factor technique to factor something like x squared minus 11x minus 26. So we need something new. We need some new machinery. We need a new technique, a new strategy to factor something where there's nothing that we can do with the greatest common factor to get the process started. So that's what we want to do today, is figure out what to do with this. So why would we want to factor something rather than leave it in what was called in the video the expanded form? So the form that this expression is in right now is expanded. Or you might call it even standard form. Standard. Or expanded form. I won't be quizzing you on that terminology, just to draw the distinction. If we are able to factor it, then here's what might happen. X squared minus 11x minus 26. If we're somehow able to factor this into a product of two things, that's what we're going to be hoping to do in just a moment. Its only real function, the purpose that we want it to serve, to be in its factored form, is that that's going to be the form in which we're able to actually solve an equation involving these expressions. So it's only really useful to us if we're using it in the service of solving an equation. Because as we talked about a couple of classes ago, if I can factor an expression and know that the product of those factors is equal to 0, that permits me to split apart those two factors and set each one of them equal to 0 and solve two simpler equations instead of solving one more complicated equation. So having something which is factored be equal to 0 lets us give each factor its own 0 and solve. So this is kind of a skeleton of what a problem like that would look like. So having this expression in its standard form doesn't give us any tools to solve that equation, to get the x by itself, primarily because the x is in two separate terms that are not like terms to one another in this expression. So there's nothing we can do without factoring at this point to solve this equation. But if we can factor what's on the left-hand side, then we can break it apart so that each factor gets its own equation equal to 0, and then we can solve each of those simpler equations. So that's the important difference. One of them gives us a way forward to solving equations, the other one doesn't. So that's why we like factoring. That's why factoring is something that every algebra student learns how to do, because it gives us tools to solve new equations that we couldn't solve before. So with all that being said, what options do we have? When you looked at either read the section or looked at the reading check video, what options or what tools do you have for factoring the expression x squared minus 11x minus 26? What would you like to do with it? So what we need is a pair of numbers which, when they multiply together, give us negative 26. So let's call that the product. Product is the result of multiplying two numbers. And that same pair of numbers has to add together the sum to give us negative 11. So that's why this method is sometimes called the sum and product game. So whatever my two numbers are, they need to satisfy the following. I'm going to kind of draw it like this here. They need to satisfy that when I multiply them together, I get negative 26. And when I add them together, I get negative 11. And it has to be the same pair of numbers in those two boxes.
2 and negative 13.
Okay, great. That pair definitely works. So we'll talk about how to go searching for these in a moment. But the numbers 2 and negative 13, you can convince yourself, fit this bill. 2 times negative 13 is negative 26, and 2 plus negative 13 is negative 11. So finding that pair of numbers is your top priority in factoring a quadratic trinomial. Some of you in the reading check question asked, what happens if those numbers don't exist? Because that's a completely valid possibility, right? Even if I change this example just a little bit, if I made this 25 instead of 26 right here, we couldn't find a pair of whole numbers that make that work. Right? So it might not always work. That's the limitation of this technique. But when it works, we'll see what to do with it in a minute. But priority number one is finding these two numbers. Find this pair of numbers. Because if you find this pair of numbers, you're 80% of the way there. Now that we have them, what do you want to do with them? All right. So every factoring problem is going to lead us to a product of factors inside parentheses. So we're going to set up a couple of big sets of parentheses and put these numbers inside the parentheses. Huh? How do I want to put these inside the parentheses? What role are these numbers going to play in the product of these factors?
Don't you set it up like how you set up the thing for 4?
Yeah. So that's
X plus 2 and X minus 13.
Yeah, you're reading my mind. So, right. What we want to do is the entire point of this technique is to reverse the FOIL process. We're reverse foiling, unfoiling, if you will, when you're factoring a trinomial. And so, because we can use this little grid technique to foil, let's also use it to unfoil. So we found this pair of numbers, 2 and negative 13. Let me put them on a couple of squares in this box. Okay. And we chose 2 and negative 13, first of all, primarily because their product gave us negative 26. The only constant term, the only term without an x in our original expression was negative 26. So that was kind of where we put our focus in the beginning, is first let's think about the number negative 26. Make that your top priority. And start your search by looking for numbers which multiply together to give you negative 26. And you could go through a variety of different possible choices. Not every possibility is going to work, but the possibility which does work works precisely because when we add these numbers together, we get negative 11. But the role that negative 11 plays in our original expression is that it's a coefficient of x to the first power. It's the coefficient of x. And so that means that probably the reason that it's playing this role is that the expressions the expression negative 11x came from adding 2x and negative 13x, if we're using this little grid to keep track of things. I think we can agree that if we add 2x and negative 13x, because those are like terms, their sum is the sum of their coefficients, negative 11, multiplied by the same variable factor, which is x. But using our grid, that must mean that this 2x that we just wrote in this box right here is there precisely because it was x times 2. So we must need an x over here. Likewise, this negative 13x, which is down here on this side, must be there as a result of multiplying x by negative 13. So what we conclude, oh, that works, by the way, also, because now what goes in this box? X squared, x times x, which takes care of the third term that we didn't have. And this argues, therefore, unfoiling, that what belongs in these factors are x plus 2 and x minus 13. So first we looked at the constant term and said, find me a pair of numbers which multiply together to give me negative 26. And there are a lot of possibilities, right? 26 and negative 1, 13 and negative 2, 2 and negative 13, 1 and negative 26. I think those are the only possibilities, but there are 4 different possibilities. And of those possibilities, which pair also adds together to give me negative 11? So the sum was our secondary concern. We worried about getting the product right first, because that's a very short list usually of possibilities. Then we worried about getting the sum right second. And once we found that pair that wins our game, then it was just a matter of making those numbers the constant terms in a pair of binomial factors where the other term is just plain x. In other words, once we knew it was 2 and negative 13, we knew that our factors were x plus 2 and x plus negative 13, or x minus 13 if you like.